All right, what's going on, you guys? Another LeetCode video today. This problem is called last stone weight. So we're given an array of integers called stones, where each stone is the weight of the ith stone. So yeah, just a vector of integers where each one of those elements corresponds to the weight of a stone. Okay, so we're playing a game where on each turn we're gonna take the two heaviest stones and then do something with them, right? So they say we're gonna smash them together, but what does that mean? Well, we're gonna choose the two greatest values, and then if those values are equal, we can just simply remove both of those values from the game. Uh, or if they're not equal, then what we're going to do is take let's see, the larger stone and then just subtract the smaller weights or the smaller stone's weight from the larger one, and then put that back into the collection of stones. So we need to do basically we're gonna have to sort the stones somehow, right? So but that might not necessarily be the best approach, because every time we take the top two stones, we're gonna have to remove them, which we might have to resize the array, which could be somewhat expensive. When we're inserting the resulting value back in, also, because sometimes when a stone is destroyed, we've got to put in a new stone, right? And that is not going to be very easy if we need to keep the stones sorted, right? So I think if you've ever heard of a heap or a priority queue, that's going to be the best data structure to use here. So let's take a look at why that's the case. So basically, if we use a max heap, that's going to allow us to be able to basically get the biggest stone. So whatever the biggest stone is, we're going to be able to get that in constant time with a max heap. We have O of 1 access to the biggest element. And then for pushing elements and popping elements from the heap, that's going to take big O of log n time, where n is the size of the heap, but that's fine, right? Because we would have to sort a vector anyways. Like if we were using a different data structure, we'd have to sort, and how long would that take? That would take n log n time, right? And it would probably be even worse, because we're probably going to have to sort several times. So this is going to be the best approach here. So big O of 1 access for the access and that's just for the biggest element, right? And then it's O of log n access, or O of log n for pushing and popping, right? So let's take a look at some examples, right? So we have 2, 7, 4, 1, 8, 1, right? So let's see, and then the output of that is 1. So if we have two, so we're going to basically be putting, the first thing we're going to want to do is just take all of these stones that are in the vector, put them into our max heap, right? So so once we do that, and again, this is a semi-sorted data structure. I don't think I mentioned that actually, so for the first time, but this is a semi-sorted data structure. So we have constant access to the biggest element in the max heap, but we don't necessarily know where the other values are. Like we wouldn't be able to access the other values in constant time. So yeah, just keep that in mind. So 4, 2, 1, 1. So that's going to be what our max heap looks like. And I circled the 8 because that's the value we have access to in O of 1 time right now. So basically what we're going to do is we're just going to pop the top two values from the stack until there's either 1 value left or 0 values left, right? So we would take this 8 and this 7, right? So these are going to basically go away, and we're going to compare them now, because right, once we pop the 8, that would be take log n time, and then we can get the 7 in constant time. So we have the 7 and the 8, and we're just comparing them. We can see that they're not the same value, right? So we're going to have to put we're gonna have to do 8 minus 7 and then put that back into our max heap, right? So we're gonna get another 1 inside of this max heap now. All right, so now we're gonna take the next top two values. So we're gonna take this 4, and then we're gonna take the 2. 4 minus 2 is 2, so we put that back into the max heap. Okay, we're gonna take a 2 and a 1, and then we would end up putting a 1, because 2 minus 1, we're gonna put a 1 back into the max heap. We have a 1 and a 1, so we can just get rid of those, right? When it's the same weight, you can just get rid of both of them. And now we just have a 1 left, so the return value would just be 1. So in terms of the time and space complexity for this problem, it's going to be, it's going to take linear time basically to put all of the, so we're gonna have to go through basically a vector linearly, right? And then each insertion into our heap is gonna be log n. So we're gonna have time complexity that's big O of n log n, where n is the size of the input vector. And then, and it's log n because, you know, in the worst case, we're gonna have to, it's gonna take log n for an insertion once all n of those values are in the heap. So, and then there's some other stuff we have to do after that where we're actually iterating through the heap, but that is not going to be bigger than n log n. That's going to be the biggest time consumer here. So n log n time complexity, and then the space complexity. I don't know why I wrote a C. The space complexity is just going to be big O of n, right? Because we're gonna, in the worst case, we're going to have all n of those elements in our heap. So just big O of n space. So let's go ahead and get into the code. So first thing is first, let's just make that priority queue. So that's how you do a heap in C++. It's gonna have integer values. We'll just use a vector of integers under the hood. And it's a max heap, so we don't have to have it change the comparator at all. So we can just call this max heap. All right, so next thing we can do is just loop through each one of those stones and that vector. So we'll say for const int, and we'll take this each stone by reference. For stone and stones, we're just going to basically be pushing each of those stones to our max heap. So say max heap dot push on each stone. Okay, so that took n log n time. And now we basically just want to loop while our max heap has, you know, at least one value in it, right? So as long as there is more than one value in there, then we can always confidently take the two values, right? And max heap greater than 1, we got to take max heap size greater than 1. Okay, so we just want to basically make sure there's two values available, because every time this loop iterates, we're going to be popping two values. So we want to make sure there's two values in there so we don't get any weird memory issues. So anyways, yeah, we made sure that there's going to be two values in there. So we're going to say, we'll have int for stone 1, and we'll just say that'll be max heap dot top. So that's going to be the bigger of the two stones. We got that value in constant time. Now to get the next biggest stone, we have no choice but to pop from the top of the max heap. So that's the only way we can really get the next biggest value there. So we're gonna have to pop, but that's fine because that'll work for our algorithm. So stone 2, again, after we did that log n pop, we're gonna have to take the next top value to get that second stone, and then we just pop again. It's another log of n operation. So yeah, so I mean, this code block is basically going to be almost n log n, but it isn't quite going to be n log n. And either whatever it's going to work out to, it's basically going to be n log n plus n log n. I'm just talking about the time complexity still, so that's why the time complexity is n log n. I only really considered this part. You also have this part, but you know, it's about the same runtime as this. And when you're doing addition, you know, big O notation, it doesn't matter. You only keep one of those expressions. So anyways, in stone 1, max heap top. So now what we're gonna want to do, right, is either these stones can be the same weight, so both get destroyed. In that case, we don't have to do anything, right? So we're really only checking if the stones are not equal, right? So we're gonna say if stone 1 does not equal stone 2, and stone 1 is the bigger stone. So in that case, they literally just want us to push a stone to the max heap. So max heap dot push, and that stone is going to have the weight of stone 1. So the bigger stone minus the smaller stone. And that was pretty clearly stated, I think, in the problem. So yeah, that's pretty much it. We just need to return something now, right? There's either going to be one value left at this point when this while loop is done executing. There's either going to be one value left, or there's going to be no values left, right? So we're going to have, let's just do a ternary, right, on this return. So we're going to return if max heap is empty, then they just said they want us to return 0, right, if there's no stones left. Otherwise, we can return the top value in the heap, which is just going to be the last element in constant time. So that's going to be the remaining stone. So yeah, let's submit this. Hopefully this video helped you understand last stone weight better. If it did, leave a like and subscribe, and I'll see you guys in the next video. Peace.